For our in-class lesson, we've decided to focus on the concept of drag. The objective of this presentation is to explain what drag is, what the different types of drag are, how drag is calculated, and how drag can be reduced. To start off with, drag is the force on the aircraft that is caused by the air resisting the motion of the aircraft. It is a mechanical force, meaning there has to be direct contact between the fluid and the aircraft. It acts parallel and opposite to the direction of the motion of the aircraft, and it can be thought of as aerodynamic friction. Three different types of drag: parasitic drag, induced drag, and wave drag.
Parasitic drag is the combination of skin friction drag, form drag, and interference drag.
Interference drag is generated by mixing streamlines between components of the aircraft. For example, the air flowing around the fuselage would have a different speed and direction than the air flowing around the external fuel tank. So, when these streamlines mix, interference drag is created.
Form drag, also called pressure drag, depends mainly on the shape of the airfoil. This force results from the pressure that the wind exercises over the cross-sectional area of the airfoil. Other variables, such as velocity and angle of attack, are important at the time of calculating form drag.
Form drag highly depends on the shape of the aircraft. It can be understood as an aerodynamic resistance to the motion of the aircraft. What happens is that the shape causes a difference of pressure, making the pressure near the trailing edge lower than the pressure near the leading edge. This change in pressure causes a force that pushes the airfoil to the back.
Skin friction drag is created by friction between the surface of an aircraft and the air around it. The Blasius friction law describes the force generated from drag in a laminar flow. Turbulent flow tends to create a large boundary layer that generates more drag.
The boundary layer of a fluid is the area in the immediate vicinity of the wing, as you can see by the image. In this area, the viscosity of the fluid begins to take effect, and the wing will begin to stick to the fluid, causing a difference in the speed of the flow. This slide shows the equation for skin friction drag. As you can see, in the equation there is the symbols Rn, which stands for the Reynolds number. This is simply a measure of the viscosity of the fluid, which is how adhesive the fluid is to the sides of the aircraft as it flows past it. Also in the equation, you'll see the symbol S wet, which stands for the wet surface area of the wing. This just means how much of the wing is exposed to the fluid as it flows past. Also, you'll note in the equation that skin friction drag increases exponentially with an increase in velocity. This means as you increase the speed, friction increases dramatically.
The pressure difference across a wing surface causes air to flow over the wings toward the base. This creates a backwards component of lift, which acts as induced drag.
This slide shows the equation for induced drag. As you can see, it is highly dependent on the lift of the aircraft, as it increases exponentially with lift. Also, it decreases based on a higher aspect ratio and a higher wingspan efficiency. Thus, wings with a higher wingspan to wing area ratio and more elliptical wings will have less induced drag.
A first way to reduce induced drag is making the wings elliptical. The elliptical wings increase the wingspan efficiency. A second way is to use folded wing tips that increase the aspect ratio of the wing as well as changing the lift direction. A third way is to use a washout, which will decrease the angle of attack toward the wing's tips. This helps to change the lift distribution of the wing to be close to an elliptical wing. A fourth way is to use wing fences that are flat plates used on the upper surface of the wing to prevent airflow along the span.
The accumulation of Mach waves on bodies flying at supersonic speed creates shock waves. Those shock waves create a pressure increase on the body, resulting in wave drag.
There are a couple ways to reduce wave drag. Thin objects reduce the accumulation of Mach waves, which creates less strong shock waves and thus reduce the drag. Applying the area rule will also reduce the wave drag. The area rule implies that there should not be any abrupt change in the cross-section area on the longitudinal axis of the aircraft, because the wave drag is essentially proportional to the change in the cross-section area. Finally, in addition to reducing the thickness to chord ratio, sweep wings will reduce the Mach number of the airflow by allowing only a component of that flow to be in contact with the wing.